Okay. This is the first part of this is just a review of state space, or so-called modern control theory, and this is the one that I gave in 5310 in fall semester. This just kind of explains the basis. You can go through this on your own. The one thing that I kind of want you to recognize and realize is that when we write something in a state space form is no magic occurs. It's simply a different representation of a physical system. State space kind of popped out of numerical solutions, differential equations, where you want to reduce the system to a series of first order equations so that you can numerically integrate it, which it is what you have to do for a higher order system of differential equations. And so it's very useful for that. Even people who don't like this will admit that that it is useful for simulation. So anyway, I go through some examples here and sort of general things, and then a couple of examples of how to write things in state space form. I also talk quite a bit about the equivalent of what we're doing here. When we talk about eigenvalues of a system, eigenvalues equate to poles in control systems. And so really, even though we spend a great deal of time talking about this is time domain, not frequency domain and everything, when we get down to it, we are talking about poles instead of eigenvalues. Eigenvalue is really, eigen is characteristic, cool German word, but we're talking about poles if we're doing systems. Now you kind of expect that to happen. The two things have to produce equivalent responses, and so. But I do want you to be aware that the state space representation is not magical. Okay, so I go through a DC motor example, and then talk about the eigenvalues. And talk about an approach to control is called state feedback, full state feedback. And so what I do is I create a control vector U, which consists of some gain matrix K times X. And then I put that in, and I end up with a new matrix here. And if I can figure out a way to manipulate K so that I can make the system respond the way I want to, then I've done what's called pole placement, and notice they don't say eigenvalue replacement, they say pole placement, so it truly is back in the frequency domain. There are methods for doing this. If you look at in MATLAB, there's, I believe it's called pole place, or if you look up just to look for pole placement, or look for placement, one line in a MATLAB command, it will pull up all the commands that do that. There's quite a few different algorithms to do this, and so you can find those and play around with this if you want. The thing I wanted to do today, though, is to spend most of the time talking about state observers. Now, there were some observations that led to observers. The first is that full state feedback can be amazing. It really can. You can do things on systems that look quite remarkable. There are kind of some limitations, however. Full state feedback requires a measurement of every system state. And so if I have like a fourth order system or a fifth order system, this would require 5 sensors. And so, as we talked about before, sensors are expensive. Measurement devices are the source of truth in a system, so I've got to invest some money in them, and this accurate sensors are expensive, and lots of accurate sensors are very expensive. So let's say that you put in 5 $200 sensors, and you've gone to $1,000 in sensors on a system quite rapidly. Okay. State space advocates, realizing the method was too expensive for most practical systems, they asked the question, can I estimate the states using a limited measurement set? So instead of instead of measuring every state to feed it back, can I come up with a reasonable estimate of the system? And they asked this question, and the answer is yes. I can estimate all of the states using a reduced subset of the system. So if I have a standard state space system and I'm measuring, this is the measurement piece of a state space system. So I have some limited set. This C matrix, it picks off the measured states, the ones that I can actually measure. And under conditions of observability, observability says that I can measure the system. I can measure all of those states. If I had the ability to, or the sensors, I could observe them. Observability, by the way, there's this really strange matrix here that consists of C transpose, A transpose C, all the way up to A transpose, the K minus 1 C transpose. And I asked the question, what is the rank of this? And if it's of rank K, where K is the system order, then in other words, this is a full order matrix. If this is of rank K, then I can observe every state in the system. This is the calculation of this is quite beautiful, but it's kind of out of the scope of this presentation. So all states can be measured, then I can obtain an estimate from that reduced set of measured states. Okay, so what does this mean? How am I going to do this? So the procedure is I have some state dynamics, and I'm going to let my estimated state equal my dynamics of the system. This, by the way, is a model of the system. It is not the system. Okay, and then I've got some scaled measurements. So I add this gain to the system and I scale my measurements. And I would like to make it so that over time, my actual measurement minus my estimated measurement becomes acceptably small. Now you're an engineer. You're the one who determines what's acceptable in the system that you're designing. So I can write a differential equation that describes the error dynamics. Okay, so E dot. And the observer model from this says that if I subtract these two, the actual, this is actual, from the estimated. So I'm just subtracting those two systems from each other. I end up with this. I've got A hat E. I've got this strange looking things times X. So this is just collecting all of the terms that multiply the vector X. And then I've got this multiplying the vector U. And this is just combining my estimator with my system. Okay, and I end up with that equation. Now we would like the error E to go to 0 asymptotically. And it seems that that's a reasonable thing to want to happen, because I want the error between the estimated state and the actual state to be 0, or are small enough, close to 0. So if I look at the dynamic equation for the error, I end up with this set of matrices has to be 0. And that set of matrices have to be 0. And this means that I have no dependence. The dynamics of E has no dependence on either the system state, right there, or the control input. And so by forcing those to 0, I can do that. And that right here says that A hat, I solve those for 0, A hat has to be equal to A minus KC, and B hat has to be equal to B. That's just saying B minus B hat equals 0 and solving B equals B hat. And exactly the same things for this. I've got A minus KC minus A hat equals 0, and I can solve for A hat equals A minus KC. Okay, so that's all I've done there. Now if I substitute this into my equation, my original equation for the observer, I substitute in A hat, and I get A minus KC plus BU plus KY. And if I look at this, this is the original system again. Okay, and all I've taken is the original system. I've got y minus cx hat, so these are the observed values. The ones I measure, observed or measured values. So these are the ones I actually have a sensor on. This is the C matrix, the thing that picks off the measurements times the estimate of the state, and then I multiply that by some value k. Okay, so this difference is the y minus cx is cx minus x, which is c times the error. Okay, and this error is referred to, this y minus cx is referred to as the residual, and it must go to 0 as ce goes to 0. Okay, so I look at this, and in block diagram form, this would be my diagram. I'm going to draw this in a little different way in a little while, but I've got y right here. This is measurements. And I've got the actual measurements, so I'll put actual here. I've got the estimated measurements. And then I have, this is a symbol for an integrator, because people who do things in the time domain don't draw things like 1 over s anymore. It shows I'm just building this system that I have here. I'm building it in a block diagram form here. So I've got this k, which is multiplying the difference between the actual measurements and the estimated measurements. And so if I choose k, I can place the eigenvalues of the matrix A minus KC. And then I've got this extra input for B there. But this then becomes an estimator. And if all goes well, when I choose K, then this will eventually settle into a state where this R, or the residual, or the error E, is pretty small. And in that case, if R is small, then I'm getting a good estimate of X, and I can then use this. A couple of things I want you to notice. This is not the system. Okay. This is a model of the system. Okay, that's really critical to this, because I haven't just tacked this onto my system. If I did that, all I do is place the poles, kind of. I don't estimate anything. I don't determine what I need for full state feedback or anything like that. So I build a model of the system out of A, B, and C, and then I estimate the states from that. So that said, how am I going to pick K? Well, I can arbitrarily place the eigenvalues pretty arbitrarily. Sometimes if I try to move them to places that are very, very difficult or require very, very high gains, my mathematics I produce what are called ill-conditioned matrices. And that means that an ill-conditioned matrix has components of the matrix which are vastly different from each other. So I'll have something that's like 1 times 10 to the 18th. And I'll have something that's close to 1, or very small, close to 0. And in those cases, a lot of numerical algorithms that you have to use to calculate with those matrices kind of fall apart. And so I have to be really kind of careful about that I don't produce ill-conditioned matrices in this. The other thing about observers is this is a model of the system. And one of the reasons we add feedback to a system is to take care of things that we don't know in the model. Does the model move over time? Does the model have unmodeled dynamics that aren't included? Is the model nonlinear? And all of those things are not incorporated in this. These are fixed values. And so I'm basically saying that is the model of my system. So Kalman filters have a habit of diverging if your models get too far separated. And divergence in a Kalman system is bad because if it diverges, that means your estimates diverge. If your estimates diverge, you can drive the system unstable. Okay, so I want to ask a question though. Is the system optimal? Or is there a gain K that I can use to make the system optimal? I kind of write a hint here for your career and frankly your life. If anyone pops up with the word optimal, the first thing out of your mouth should be with respect to what? Optimality is kind of thrown around very loosely in science and engineering, and you've got to know with respect to what. Why is it optimal? When I first encountered an area in controls called optimal control, I was so excited I could hardly stand it because I thought, oh, I'm going to be able to design the best controllers, the best systems. And then I found out that the word optimal means different things to, it's based on something you're minimizing. There is no global optimality in general. And so I'm saying the best, the greatest, that sort of thing, but I'm saying with respect to, in terms of optimal control, with some pretty arbitrary cost function it's referred to. And so, but in terms of optimal estimation, Kalman and Boosi approached this problem, and it was in the late 1950s. And previously, the Wiener filter had approached this problem in the frequency domain. But Kalman decided to approach it from a discrete time domain approach. And the filter I'm going to show you, however, is going to be a continuous time domain Kalman filter, because you can find discrete Kalman filter information everywhere. And so what they did is they said, well, if we have noise added to the system where V and W are white noise, zero mean processes. And white noise means that it has a flat spectrum, and in general the noise process will just look random. Okay, and in fact, random number generators, true random number generators, are pretty good white noise generators. Zero mean means that it has no average, non-zero average component, and then it has known spectral density matrices. Those are all the requirements that Kalman and Boosi put on this specific filter. And so if that's true, adding these processes, this just means that my processes have additional noise, and this is a process noise, and this is a measurement noise. Okay. Okay, so optimal state observers. There's some really beautiful mathematics involved in this, but it's beyond the scope of this presentation. The optimal gain for the Kalman estimator turns out to be this. This is the error covariance matrix. This is your state space C, or your measurement, and this is the inverse of your power spectral density matrix, and that is your optimal K. Now, if you know all of these things, you can simply sit down and calculate your K. Unfortunately, you likely don't know this, okay, because this is based on the error. However, the optimizing covariance matrix has these dynamics. This is a series. This is the A matrix of your model of your system, and again, here's the P hat is the error covariant, or the optimizing error covariance matrix, and then you've got everything here. This is your process noise multiplier, and then this is the power spectral density of your process noise. So that process noise vector that you had right here, and the F they had there, those incur there. So officially, in order to create a Kalman filter, I'm going to have to solve this thing, and There's a couple of things that you can do. One of them is you can assume that it's at steady state. If I assume it's at steady state, that means that p hat dot is equal to 0, and then I just have this equation to solve. And so I can solve that one. Now, what you'll notice is that this optimal gain, as long as p hat dot is not 0, this is changing. These two, as long as the process hasn't changed, process noise hasn't changed, are going to be constants, and I use that term very loosely. This, however, will be moving because this is changing. And so that means that your Kalman gain in your system is going to be changing. If your Kalman gain is changing, that means that it's moving around, trying to find some spot to settle to, and which it will do. Now, the adjustment of K, they're dependent on another dynamic system. And so the whole system that you end up here with is nonlinear. So as I say, if you're both lucky and good, system will come to a steady state, which you're hoping. And in the steady state, this is 0. This is called the algebraic Riccati equation. It's famed in Song and Tale. This also comes into optimal control. This is called an ARE, okay? And it means nothing has changed. Okay, this can be solved for p steady state and p hat steady state and k hat steady state, and these can be used to calculate the value using the observer. Okay, there is a discrete equivalent of this also, and so we've got to be concerned about that. And however, given a state space model with sizes next to the vector, I want to draw kind of some pictures so you'll see what's going on here. This is, I'm showing the sizes of the matrices and vectors here so that you can kind of get an idea of what sizes. They don't necessarily have to be square matrices. You've got an L by N here. This one's N by N. This one doesn't necessarily have to be a row matrix. It can be N by M, and you can have multiple inputs. Okay, the state observer can be represented by a block diagram on the next page. Okay, so for the optimal observer, the only thing that differs from the one I had before is I've shown these lines as being vectors. The one thing is the Y lines represent vectors, and the matrices pre-multiply their inputs. So this will produce CX hat out here, okay? And we only have measured L of the n available states in the system, but the observer will estimate, in that case, the remaining n minus L state. These estimates are then used in a full state feedback system. Again, I want to emphasize this whole thing, the B, C, A right here, is a model. It is not the actual system, and that is critical for you to understand that, because this is not something you tack onto the system and hope it'll work. You have to build a model of the system in order to use this. Okay, so from that, it hides some complexity because this block right here, labeled K hat, has to be calculated, and K hat is from this. Okay, so these are matrix multiplications that I'm going to have to use. Now, the term p hat is defined by that matrix differential equation that I had right here. Okay, so this equation right there is the matrix differential equation, and you have to write drawing a diagram for that in diagram form so you can see that. This is p hat dot right here. This is everything that makes up p hat dot comes into this summing junction. You notice these are vectors. All of them are vectors. And you have to get all the sizes right and everything, of course. But you've got, just building this equation, you've got a p hat. Then you're going to have to use some transposes. And as I say, I get kind of giggly here because the math is getting really pretty hairy. And then I've got this weird state here where I'm going to pre-multiply this thing by p hat again and add that in. And then I've got this constant that I add in, or I subtract off the whole thing. The reason I say I get giggly is you can just count up the total number of matrix multiplications you're going to have to do in this case, and it gets pretty hairy. Okay, so in order to implement, however, a Kalman filter with adjustable variable Kalman gain, this is what I'd have to do. Okay, one of the things that happens, I was looking into some GPS filtering which uses Kalman filters, and the guy who wrote the book about it said that you have no right to use a Kalman filter unless you know what your what is it called, spectral matrix, anyway, your power spectral density matrix. You shouldn't use one unless you know what those are. And the reason is because Kalman filters are designed to minimize the estimate error based on white noise, zero mean processes. And if your processes aren't white noise, zero mean, then it's not optimal. So I always laugh when I hear people saying I'm tuning my Kalman filter, because what that means is they're making adjustments to K hat in order to get a better response out of it. But that immediately means that they don't know what their noise properties are, or they may not be random or white at all. And so the whole tuning the Kalman makes me laugh. And so, because Kalman is supposed to be an optimal filter, and if you're tweaking it, that means that you're playing in another domain. And so a lot of people are convinced that the only thing you can do is Kalman filtering. However, that is not necessarily true, and I'm going to be showing you some alternatives to Kalman, and we can talk about those in the next little while. Okay, hope everybody's safe and healthy.